So we need to get some nice massive stars that will eventually become supernovae and produce these heavy elements. The trouble is, after the Big Bang, all we had was a very hot glowing fog, as you remember. This is a diagram of the microwave background radiation showing the lumps, but this is kind of a cheat. We've scaled this up enormously by 100,000 times. A true image of this, as it would look to us if we had microwave eyes, is extremely boring. Ta-da! So we've got to turn something incredibly uniform into something very lumpy.
So the way we normally do this, because it turns out it's very difficult to calculate the equations of gravity just from scratch, is we go through something called nbody simulations, where we break it down into a bunch of little pieces, which we can do on the computer. So Paul, why don't you tell us about that?
Okay, so how do we simulate the formation of the first objects? This is done using what are called n-body simulations on a computer. We've already seen an example of this in the previous lesson when we were talking about fluctuations. So let's say we want to simulate a part of the universe. First of all, let's set up some coordinates. Let's call them x, y, and z. And then we'll have to put a whole bunch of objects, n objects, hence the name, n bodies. And each object will have a coordinate x, y, and z. So in your computer, you have object 1, so 1, 2, 3, and you have position x, y, and z. And you'll give each particle numbers for those. Then you'll also need its velocity. To begin with, the velocity is going to be quite small, and the velocity will also have x, y, and z components. So you pick all your particles, particle number 1, particle number 2, particle number 3, particle number 4, particle n, where n is going to be a large number, and for each of them you give them positions and velocities. And to start off with, those positions and velocities are going to be such that the particles are spread pretty uniformly everywhere, with just a very small amount of lumpiness. Now what we do is we have a whole series of time steps. We know where everything is at time 0, the starting time. What we then do is work out where they're going to be a little time later, a time delta t later. And we keep doing that, moving them one little step at a time. The method we use is approximate. It won't give an exact motion over delta t, but it will be close enough that if you make delta t small, you can see what's really happening. So what do we do? Well, let's say we know a given object has a position x, y, and z, and has velocity vx, vy, and vz at time 0. Where's it going to be at t plus delta t? Well, the simplest approximation is just to say that the new position will be x, the old position, plus the velocity times the time. That's actually the definition of velocity. Velocity is the rate of change of position. Likewise, the new y is going to be the old value of y plus the y velocity times delta t, and the new value of z is going to be the old value plus z velocity times delta t. So that's just saying if the particle is here moving in that direction, velocity in that direction, after a time t, you just take this position, add that position, and it'll be over there. So it's just at each delta t, it'll keep moving like so. Now, if there was no gravity, that's all you'd need. Every particle would just keep on moving in a straight line. But there is gravity. And what that's going to mean is the velocities are going to change. So take, for example, this particle here. It's going to be gravitationally attracted towards that particle, this particle, this particle, and so on. And we can work out how strong that gravitational pull is. So this particle here is the closest. We can calculate the distance. Let's say this was particle 1, that one's particle 2. The distance between them is just going to be the square root of x1 minus x2 squared plus the same for y and same for z, Pythagoras' theorem. So that will tell us what the distance here is. Once we know the distance, we can now calculate the force, which is just going to be given by Newton's law of gravity. G, mass of the first object, m1, m2, over the distance, squared. So what we can do is for each particle, we can then go about every other particle and work out the gravitational force. So in this case, this will be the closest, so there'll be a force pushing in that direction, which is quite strong. This particle is further away, so there'll be a weaker force in this direction, a force in that direction, and a force in this direction. So we get all the forces of each particle and every other particle. It's a lot of arithmetic to add them all up, but that's what computers are good at. And so we can work out the total force, which is just the sum of the individual forces from every other particle. Once we've got that, we can then work out the acceleration, because we know that force equals mass times acceleration. So the acceleration is just force over mass. So as we know the acceleration, we already know how to work out the new position. We can also work out the new velocity. The new velocity in x is going to be the old velocity in x plus the x component of the acceleration times delta t. The new velocity in y is going to be the old velocity in y plus the y component of the acceleration times delta t, and so on for z. So that's what we do. We start off with everything in their starting positions, which are very uniform. We pick a small time step, and for each time step, we calculate the new positions. We calculate the gravitational force by adding up the forces of every particle and every other particle. That's what takes most of the time with the computer, hence the acceleration. And then we update the velocity. So we now have a new position and a new velocity. So back in our computer, we start off with the initial positions and velocities. We get new ones. And then we do it again, and again, and again. And so step by step by step, every particle moves with its position and velocity constantly updating. Now I've put together a simple code to show you that using the Visual Python library. Let's have a look at that. You can take this code and edit it yourself. Hopefully it's well commented enough. This is going to simulate a spherical region of the sky. And what it does is this part of the code here tells us where everything is going to start off. It distributes the points randomly. And then it does a loop. It works out the force of every object and every other object. Updates the positions. In this case, I've also added the expansion of space. So I've got a scale factor that gets bigger to allow for the fact that while this is all going on, space is actually expanding. So that's what it looks like. Let's run the code. So you see the particles start off pretty uniform, but they're slowly being pulled towards each other. This is a 3D simulation, so you look at it from different angles. So there's a whole bunch of particles here being sucked towards each other. This code is set up so that when particles touch each other, they merge and form a new single bigger particle. So you can see some big particles forming over here as they swallow other stuff. So it's not looking quite so uniform now. You've got some big particles that have swallowed stuff and other smaller particles. And there are still more collisions going on. So as time goes on, we get more and more. You see we now have got a dense region over here, a dense region over here, and probably an empty void over there. Lots more collisions going on. So this is showing gravitational instability at work. And you get different answers if you change the expansion rate of the universe, change how lumpy the things were to begin with, and you can play around to your heart's content. That simulation was a trivial little thing, simulating only 400 particles on my own laptop. Real researchers in this field will use many months of supercomputer time to come up with simulations like this one, following often several million particles over millions of years at far higher precision.